In this class, we study properties of waves, and our main theme is the interference. The big difference between the particle and wave is that the superposition of wave function, and it is because the particle, when two particles collide, depends on the impact parameter. It can make a head-on collision and it returns its original path to collide. Or if there is some impact parameter, non-vanishing impact parameter, then after the collision, they scatter with the scattering angle. Anyway, two particles are at its own place, and they do not overlap. But in the case of wave colliding two waves, because the wave is just a displacement of an object that is a single oscillator among multiple oscillators that are weakly coupled. When they collide, the displacement of a particle that is not moving left and right slightly, but uh, its a deviation is to be added when they collide. So two wave collides, then the resultant wave is something like the sum, the algebraic sum of two waves. This is just addition of two vectors. Okay. When we add two vectors, if they are parallel, the resultant vector is a doubled. When they are opposite direction and of equal magnitude, they just cancel. So this superposition principle for the vector addition is applied to the interference of wave. That is the big difference between the wave and particle. So we shall find that solution of wave is called the wave function that describes the displacement of an oscillator from its equilibrium position. When we add, we have resultant wave sometimes disappears or sometimes doubled. To understand the interference pattern of two interfering waves, it is good to study the interference of two sinusoidal waves. A sinusoidal wave has a definite wavelength, a repeated pattern. After the wavelength, it's a period in time and in space. The periodicity is expressed in terms of wavelength lambda. And the sinusoidal wave is a periodic. For, for that reason, it is a very simple to deal with. In addition, because a wave is a collection of simple harmonic oscillators that satisfies this equation of motion, this, the solution of this is a sine function, sinusoidal function. So we use the omega t minus delta, something like that. This is the time dependence of a single oscillator. But if you have many oscillators, this phase shift becomes a function of position, r equals 1 to n, something like that, k. Then it is then expressed as a kx minus omega t style. Okay, so this is the reason why we frequently use the notation sinusoidal function for wave functions. So in case we have lambda and t, lambda is a period in space and the t is the period in time. If both lambda and period are identical, it is a constant. In that case, we call it the coherent waves. If two waves are of equal wavelengths and of equal frequency, then we can make use of the simple relations for sinusoidal functions. In case we have a cosine, two cosines, identical cosines except for a phase difference, then we can define kx minus omega t and kx minus omega t plus phi as half of pi subtracted by half of pi plus half of phi. So this cosine, this is alpha, and plus alpha minus beta, and this is a cosine alpha plus beta, where alpha equals to kx minus omega t plus 1 half phi, beta equals 1 half phi. If we expand this one, cosine alpha, cosine beta, plus sine alpha, sine beta. And this one, cosine the same, and minus sine alpha, sine beta. So if we add these two, what we find is 2 times cosine alpha, cosine beta. If we substitute these numbers, you have 2 times the cosine half of phi. It is a very important factor. And the cosine kx minus omega t plus half of phi. We find that this is the average of the two. This kx minus omega t and kx minus omega t plus phi, add them up and divide it half. Then you will find this is a kx minus omega t plus 1 half phi. This is average of the average of the argument appears as the same form, cosine. It used to be cosine, then resultant wave cosine, except that the amplitude is modified from identical amplitude A 2 times A times cosine half of phi. And if you make use of a sinusoidal function sine function, the structure is exactly the same. Even though we use exponential function, still be the same. Average argument is the average of the two arguments, and amplitude is twice of the amplitude multiplied by cosine phi. This cosine 1 half phi determines how the resultant wave is. Everything else is fixed, but this varies depending on phi. Sure, it varies, but it is just a translation. Shape doesn't change at all. However, this one determines the change of the shape. Geometrical viewpoint, we have two amplitude that can be described as a two-dimensional vector with the same magnitude, except that the radial vector is obtained from the x-axis by rotating angle alpha and alpha plus phi. The sum of these two vectors, you notice that because the length is the same, this object is a rhombus, and diagonal of this rhombus can be calculated. This is two congruent isosceles triangle, and we have phi, and this angle is become half, and this is a. right angle A, and this angle is 1/2 of phi. This length is A cosine half of phi. Because this is this, and we need twice of this, so the amplitude, resultant amplitude equivalent is equivalent to the resultant vector that makes angle phi. If there is angle phi, the same vector with the same magnitude, the resultant vector is 2 times a. The a is the magnitude of each vector, and cosine 1/2 of phi, and direction is just a double prime, that is alpha plus 1/2 of phi. This is alpha, and this is alpha phi. Okay, we have studied, we learned that the two-dimensional Euclidean space, two-dimensional Euclidean vector, and complex numbers have the same geometric structure. So this is exactly the same. This is exactly the same, except that we just replace the Cartesian unit basis vector with the exponential I delta or something like that. So next we consider the overall vector that depends on the phase difference. This one becomes one when the phase plus minus one, when the phase is 2 and pi. We say it is they are in phase. If they are in phase, the amplitude is twice, because it becomes either plus minus one. The amplitude is twice the original amplitude. We call this as a fully constructive interference. And the other one is a fully destructive interference, when this one vanishes when it is a multiple of odd number. Okay? Odd number multiplied by pi. This is even number multiplied by pi. So it is, we call it completely out of phase, and it is in phase. In phase, fully constructive; out of phase, fully destructive. Another interesting feature of interference pattern is standing wave. And standing wave is for a collision of two waves. Collision of two waves. One wave is propagating to the right, and the other wave is propagating to the left. And for simplicity, we consider identical wave function style, except for the fact the center of the two wave packets are well separated, and they are traveling uh, the, each other toward each other to make a head-on collision. The interference pattern is the same in logic. The difference, the only difference of the two waves are the difference in the velocity. You know, kx minus omega t equals if I k factored out, it is omega over k t, and this is velocity. So k x minus vt. X minus vt propagates to the right as time flows, and the x plus vt style, that is propagating from the right to the left. The sum of these phase, sum of these two phases is 2k dot x and phi, and we average this. to find the k dot x plus 1/2 phi. That appears as the same function. This is a cosine function. If it is a sine, average, exponential, average. And then overall factor is difference. Difference of these two. Let us subtract this one from this. Then what's that? This 2 omega t plus phi and 1/2. This is omega t plus 1/2 phi. Omega t plus 1/2 phi. And this is always cosine. So the difference can be this one subtracted by this or this one subtracted by. In either case, cosine is an even function. So always cosine omega t plus 1/2 phi by, that is difference divided by 2. So that is the same for every case. It is identical. Cosine is common for cosine, sine, and exponential. And there's a factor of 2 because we are adding 2 waves. Important point in here is time dependence and spatial dependence are separated as a product. Time, space, time, space. This means that this wave function is not the form of x minus vt. V is a 0 here. Therefore, it is not propagating. That's the reason why we say it is a standing wave. It's a standing up and down, up and down, up and down, up and down. So this time dependence says this is a spatial dependence, and time dependence just changes the height. Up and down, up and down, up and down. So there's a standing wave. It is not working wave. It is not moving at all. It is isolated. This sine wave is not moving. Instead, it is the size, only the size is growing up and shrunken, growing up, shrunken. This is a standing wave. So in a standing wave, there are points that does not oscillate at all. This is called the node. And there is a point, there are points with spatial derivative vanishes. These points, we say it is anti-node, and these are nodes. Okay. Reflection at a fixed end can be explained very simply if we consider two waves colliding, but they are identical except that this is an odd function. An odd function f of x equals f of minus x. We have negative sign. Any function can be expressed in terms of even part and odd part. This is odd. Any function is a superposition of even part and odd part. In case it is absolutely odd, this one completely disappears and it is expressed as f of x only. And we find this kind of shape. This is an odd function at some point, at some time, and as time goes on, it propagates, and still it is an odd function. So let me just look at the point x equals 0. then f of x minus vt psi of t and x equals this wave function is will plus f of plus vt and negative sign. If I substitute x equals 0, then vt minus vt. Okay, this kind of stuff. And it's better to write it as a, wait a second. I have added some more. This functions f should be even function. So even function with respect to its symmetry axis. So, and the same function, but it is opposite. It is subtracted. This subtracted. If I this is the point x equals 0. If I substitute x equals 0, psi t0 is f of minus vt subtracted by f of vt. Because it is even, it is always 0. So as it propagates, the shape, the macroscopic shape changes. However, this point is always fixed to be 0. So this one becomes a node in any case. So finally, we can say this x equals 0 is a node. This is the explicit resultant waveform depending on time. In any case, this fixed point cancels exactly. So in any case, they are out of phase. To make a complete cancellation, the destructive interference. So if we remove the remaining, the right part, right, forget about it, look at the left side only, then we can see a wave reflects against the fixed end. Fixed end means it does not oscillate at this point. So x equals 0 is a node, and it is a fixed point, fixed end reflection. When the reflection of wave happens against the fixed end, the reflected wave becomes completely out of phase. Okay? Out of phase, opposite direction. All right, next one. At fixed end, we still use the same even functions f to describe the wave function psi. In that case, if we substitute t equals 0, f minus vt equals f vt plus equals 2 times f vt. So in the middle, it is always a double of a single wave function. You can see when they meet together, it will be double. So two waves are in phase, and if you forget the right side, the reflected wave has the same kind of form. So the x equals 0 is to be anti-node. So in summary, you can see when the two waves of in phase collide together, the midpoint is always an anti-node. And when they overlap exactly, then the wave becomes double. So there is a flag, wavy flag, And this is a flagpole, flagpole, and there's a flag. You can see this oscillation, but at the open end, there's a wave reflects, but it is a wave reflects in phase. So after the collision, it reflects the reflected wave has the same form. It is in phase, but at the end of the open end, the oscillation is maximized. So when it arrives at the end, the wave arrives at the end, it is something like, okay, this side, this side will be doubled, doubled. Okay, so this is the reason why it is way beyond the time and it is not likely screwed up. That is the effect of reflection of wave at the open end. The amplitude is doubled. Resonance, we have studied in the previous class that wave can be understood as a collection of many harmonic oscillators that are weakly coupled. And the resultant wave is a linear combination of many normal modes, and normal modes has a frequency. In the case of lower lying frequencies, they are multiples of fundamental mode, the fundamental frequency, and this is called the fundamental harmony. And excited states are n equals to 2, 3, something like that. And these harmonics are multiples of the fundamental frequency. And Pythagoras understood this for the low lying frequencies, but in fact is we have a sine function. It terminates there is a cutoff frequency. The higher uh, upper limit is not unlimited but limited. So sine function dependence makes it more complicated. But as far as the lowest lying frequency is concerned, Pythagoras was right. The expansion of the general wave function is a linear combination of harmonics and some more. And they are multiples of fundamental frequency. The fundamental frequency has the eigenfunction, eigenfunction of this shape, and next order we have eigenfunction of this shape and this shape and so on. And linear combination of these various signs, so these signs of various period, if we include the shorter periods more and more, the approximation becomes more accurate to the original wave function. Sound wave is a kind of longitudinal wave that the oscillation is up and down. Instead, this oscillation, uh, if we choose the direction of propagation, horizontal direction, and the wave that oscillates perpendicularly to the direction relative to the wave propagation is called the transverse wave. Transverse wave. However, if the oscillation is along the longitudinal direction, we say it is a longitudinal wave. And the sound wave is a longitudinal wave. That means we have air and there is some piston like there's a speaker. Speaker has a membrane, it vibrates, then the density of air changes. Accordingly, the pressure changes, and the change of pressure propagates along the longitudinal direction. So at some point, it is the air is more dense, dense, dense. So there is a periodic structure appears. In order to do that, we have a variable rho, variable pressure, and variable volume. To simplify our analysis, we restrict ourselves for the air trapped inside the cylinder. Then the cross-section is fixed. Simplest. Cross-section fixed. When we consider Bernoulli's equation, we consider the fluid that is not compressible. So non-compressible fluid, that means volume doesn't change. So rho, V, theta constant. In order to consider the wave propagation, this one is not adequate because density, pressure, volume are all varies. Instead, we can think about the steady state. The vibration, it becomes a kind of standing wave and sound distributes over space with the variable pressure, but the time dependence is averaged out and it has a steady state. Time dependence disappears. So in this limit, continuity equation is the most general one that doesn't care whether it is a non-compressible, incompressible or not. So it is always true, but we take the steady state limit. In that case, time derivative, partial time derivative of density, although spatial dependence of density and pressure may vary, but partial time derivative vanishes. Still, divergence J is 0. If divergence J is 0, divergence theorem can be used. The flux over its volume over the surface, closed surface surrounding this volume must be 0 too. And because we are considering air trapped inside the cylinder, the cross-sectional area is invariant. We can pull this cross-sectional area and surface J dot d sigma. So this J dot n equals 0. That means the right side, left-hand side, the J dot n, and these two n's are different. This is n, and this is n. So relative to the current, They are opposite. So let me write it as a j of x here, jx plus the dx here. Then the integral is a jx plus the dx minus jx because of n is heading different direction. So this is the difference, this difference between the two ends of a cylinder of height dx. Anyway, this one must be 0, must be 0. Then what is j? J is rho v. In the derivation of Bernoulli theorem, Bernoulli equation, we consider case rho is a constant because incompressible. But here it is compressible, so it is not constant anymore. The J is a constant. J is constant. That means rho plus dx, Vx plus dx equals to rho x Vx. It does not mean it is a 0. So both the rho and V vary, but the product is constant. So if the product rho V, this product is constant, then we have d rho V plus V d rho is a 0. Because of this, this velocity direction is fixed, so I don't have to keep the vector expression. This can be just a scalar. From this, I can take the ratio. D rho over rho, so dv over v, but we have negative sign. The reason is that the product rho v is a constant. If it increases, this one decreases. If one decreases, velocity increases. So it is an opposite sign. So dv over v, that is the velocity difference between the two ends. Here we have a v, and we have a v plus dv on the right side and the left side. V over dv, if I multiply a dt on the numerator and denominator, this one becomes volume. This one becomes a dx. So a times the dx is the volume. Here, av dt is the volume. But we have a single dt to this is dx, and dt dv. This one is a change in dx, change in dx, change in thickness. So change means we have air contained in the dx, but because of the pressure difference, there is a slight change of the dx. So change in dx. So that means the total volume inside the cylinder divides the amount of volume that varies because of the change in pressure and change in velocity. They are equivalent. Change in density is opposite to change in velocity, and that is just change in volume of this total divided by this volume. Okay, that's a slight change. Okay, variable velocity between two ends of this small amount of air gives the density relation, density, velocity, and volume relation. They are all proportional to each other. Note that still we have negative sign in here. If volume increases, density decreases. If volume decreases, density increases. Mass does not flow out. Okay. With these relations, we can construct the equation of motion for the air contained inside this volume. This is a volume V, and slight change in volume dV. If the dV appears, and this is proportional to minus pressure, minus density. Okay, so we have obtained everything. There is a pressure at x and pressure at x plus dx. If I know the pressure multiplied by the cross-sectional area, I can find the force. The problem is that pressure does not have the direction, but surface has the direction. They are opposite. So if I add these two multiplied by area, then I have difference in the pressure. P x plus dx, this normal direction is in this direction. On the left side, normal direction of the surface to the left, so they are opposite. The change in pressure can be evaluated in this, and the net force is toward, this is F in this direction, and this is F on the right. Okay, so F on the right is x plus dx. F on the left is a times p of x. So if I sum them up, the difference between the two ends, left hand, this f of x, this f of x plus dx. This is the right direction, this is the opposite direction. Okay? So this is acceleration. Acceleration is to be multiplied the mass inside contained in the cylindrical container. This is the mass of that dm is in here. That equals df, the difference. And that difference is area times dp. This one is a px plus dx. That is p of x plus the dp. And this side pressure is p of x. And area multiplied by area, these two cancels, only this survives. But on this side, the force should be on the opposite direction. We have the negative sign on it. So acceleration is a positive only if left side pressure is greater than the right side pressure. This is stronger and weaker. That means the pressure must decrease. Acceleration is positive only if the pressure must decrease. That's the sign we have negative sign in front of dp. So everything is ready. And next step is just straightforward. We have identities. Once we have constructed the equation of motion, we have the ratio v over dv over v. So we divide both sides with V and multiply dt to the right hand side. And then finally we obtain this ratio. And summarizing the equation, we have velocity both sides and move this one in here, and V squared equals dp over d rho. Okay, pressure increases, volume decreases. So we have identity, the pressure relation, this relation that is to be replaced with velocity, density, volume, this relation. So pressure is to be replaced with, in here, pressure is here. We have inserted this relation simplifies this one as the form. And actually, we find the ratio. This ratio is the stress to strain ratio. Compression stress divided by compression strain. That is what? That is a bulk modulus. And density is for the volume mass density, so mass per volume. So everything is done. So speed of sound is a square root of bulk modulus divided by density. In the case of string vibration, we had tension over rho, and this rho is a mass density per unit length. In summary, speed of sound in the square root of bulk modulus divided by the density, the volume mass density. And the negative sign important. Pressure increases if you press down, then the volume decreases. This volume is positive, but change in volume is negative, so I have to put the negative sign on it. And that is a way to define the bulk modulus of air. And it is different from what we have done with the derivation of a Bernoulli equation. Bernoulli equation assumes the incompressible fluid, but it is a compressible fluid. Only if it is a compressible, the finite bulk modulus, it can transmit the sound. The density in space must vary. Okay, that is the way of transmitting the sound in the air. And this is another theoretical summarize that you can follow by yourself. Important point in here is you can see the pressure, change in pressure, result in change in volume. This is positive, delta V is negative, and change in volume is there used to be psi of tx at x point, and we have translation by dx, and there used to be some function or value. The wave functions has its own value, but due to the pressure, this amount changes a little bit. That that change is related to spatial derivative. Therefore, the displacement, there's a spring, for example, if we can consider it as a spring mass system and longitudinal motion. And if the displacement is bigger, and there used to be this mass in here, but now it is has been moved to somewhere else. This is empty. Empty. That means the displacement of a mass means decrease, empty, decrease of the density and decrease of the pressure. Okay? Therefore, the pressure is proportional to the derivative of wave function. That's a good point. Pressure is, change in pressure is proportional to the spatial derivative of the wave function. So pressure is not proportional to wave function. That's the good point. And that wave function is the shifting oscillation from the equilibrium position. If it is at the equilibrium position, pressure is the maximum value. And it is a maximally displaced, then the pressure becomes minimum value. So they are out of phase. If it is cosine, it is sine. Okay? If it is cosine and this one is a sine, and this one is a sine, this one is a cosine. All right? This wave function is a cosine, then the pressure change is a sine. In addition, by definition, I can substitute this one amplitude with the cosine function. If I substitute, it becomes a sine function, and the relation of the velocity, bulk modulus, and density relation, this gives bulk modulus is rho v squared. I have replaced this bulk modulus with rho v squared. And then I can make use of the relation, dispersion relation. This omega over k is the velocity, and I can kv, I can replace kv, single power of v, with omega. So density, angular frequency, velocity. This product is proportional to pressure. And in addition, wave function is known, then pressure has out of phase. It is one half pi has been shifted. We have an experiment of complete destructive interference between the two speakers in a pipe. This generates a sine wave, this generates sine wave, and then suddenly the sound disappears because of the this complete destructive interference. Then you have to know the pressure dependence, not a displacement of a wave function. Okay? Because the sound is related to the pressure and the speaker vibrates it changes the pressure. Okay? This one can be applied to two open ends. Previously vibrating string problem we used two fixed ends. And these two open ends, they have antinode in here, the node is in here. And this is a wave function. It is not a derivative wave function. If you want to consider the sound level, it should be replaced with the pressure formula. Pressure formula is psi, round psi over round x instead of psi. This is a psi. This is wave function. And they have a family of harmonics. This is a fundamental harmonic, and so on. In the case of one open end, psi vanishes. If you want to transform into the air pressure is proportional to derivative of psi. Next, we consider beats. Beats is very similar to the interference of colliding waves, but this is parallel. They do not, their propagation direction is the same. The only difference is a slight difference between the two lambdas and two periods. And k equals 2 pi over lambda, and omega equals 2 pi over period. And there is a slight difference. That means k1, k2, k2 equal k1 plus delta k, something like that. Anyway, when they are similar, in any case, cosine addition will give the cosine for the average of these two. Average, this is average, and this phase is also average. And difference appears as cosine. Okay? Same function with average, always cosine with difference of half. Okay. When they are similar, this difference is much smaller than the average. The average is much bigger than the difference, right? So the period, in, we know V equals omega over K, that means V constant, Vk equal omega. So K and omega are proportional to each other. Therefore, the basic structure is uh, the same for K and omega. And we consider at a single time there is a wave like that. This is a small one, and this is a large one. Large one is a shorter period. Shorter period oscillates, oscillates, oscillates. So we say this is envelope. One envelope is just half of the period of longer period. The difference is a longer period. And this period is smaller. It fills the, the envelope. Envelope contains many sheets of papers, right? So that's the reason why we call this one as envelope. This is true for everything, whether it is cosine, cosine, or sine, or exponential. The original function with the argument of average and 2 times cosine of difference multiplied by 1/2. They are identical. This kind of effect is called beads. Ooh, ooh, ooh. Okay? Beads. So beat frequency, actually this is the period, actual period, but our ear cannot distinguish the rising up and going down. Then our ear is sensitive only to the magnitude, the square of this function. So even though actual period is this, we our ear treats this is the actual period of beat, just only 1/2 of it. So beat frequency is double. Frequency is double in comparison with the actual frequency. That's because our ear does not distinguish the difference. Right. Doppler effect. We have a medium that transmits the sound with the velocity v, but if the source is moving, the wavelength, this is a wavefront, wavelength varies. If source is moving, wavelength becomes short, and behind wavelength becomes longer. And if the detector is moving, the relative velocity, the propagation velocity changes. It is all in the frame of medium raster frame. It is moving with v, but if we move the detector moves relative to the wave, then as a result, the frequency changes. So because of that, the complete formula for the changing the frequency of hearing the sound is expressed in this way. It is a vector notation. For example, if you move away with the velocity greater than the speed of sound, you can never hear the sound. Okay? Self-test, you can review this. This is the equation of motion for the vibrating string we studied in the previous class. So at the end, we consider the cutoff frequency. Okay, that's it today. Thank you.